Good evening. Welcome to the August meeting of the Baton Rouge Astronomical Society. Tonight our guest speaker is Dr. Tabitha Boyajian. I never can pronounce it correctly. But anyway, she's going to be talking about what she's been named after, Tabby's star, and other interesting developments and stuff. So, Tabby?
Thanks so much, John. Can you hear me fine? How about here?
We'd have to get feedback from our online community.
All right, we'll just go until they.
Oh, Lily says she
Okay.
can hear you fine.
Yay.
Thank you, Lily.
Okay. Thanks so much. All right. First of all, thanks for having me out. I think it's been too long since I've been out here to visit you guys. And I wanted to kind of tell you guys this story that maybe some of you are familiar with, but maybe not all of you, about this crazy star. And we actually have a logo for this star that's shown here up on the screen. And this logo kind of symbolizes several different things. First, it shows an eye, and the eye symbolizes how this star was actually found. It was found by human eyes looking through NASA data, and that people identified with their eyes that something was really weird going on. The second thing it symbolizes is in the middle, in the pupil, is what these humans picked out that was so strange. It's what we call a light curve. So this is how a star's brightness changes with time. And instead of being a straight constant brightness, you see these variable ups and down parts. And then the last thing that this logo symbolizes is that we want to watch this star to learn what's going on. And that's kind of our main objective, kind of like from when the star was discovered up until this point into the future. So I called this star Where's the Flux, or WTF. That's my nickname for it. Other people have nicknames for it. But now I have this cartoon, image saying like, okay, well, where is this flux? And flux in astronomers' terms means brightness. And I'm going to tell you kind of a story about that and what it means and what we've learned so far. So a bit of background first. The star was identified through the citizen science platform called Planet Hunters as part of the Zooniverse collaboration. And it calls on volunteers from the general public to classify light curves from the Kepler Space Telescope and the NASA Space Telescope, or the TESS Space Telescope, to search for transiting planets. Now, this uses the human brain's ability for pattern recognition. And what our users are trained to do is search for dips in a star's brightness. Let me turn on decline. Sorry, that was really bad. I'm getting calls on my computer. I'm going to turn on Do Not Disturb. I haven't taught in like months. I totally forget how to do these things.
That's important.
Oh, wait, no, that's not Do Not Disturb. Hold on, that's airplane mode. I'm so out of
We'll
focus.
try not to show this to your students.
Focus. Yeah, Do Not Disturb. Okay. Now, getting back to things. Okay, so what we're looking at here. So the Kepler Space Telescope, and now it's flying the TESS satellite, is NASA missions that were designed to do the most boring things that you could think of. They stare at a single patch of sky continuously forever, right? And they measure the brightness of like a couple 100,000 stars. And they take brightness measurements every 30 minutes and they watch for something to happen, right? And if there's a chance alignment for a planet that's going around one of these stars, you'll see periodic drops in the star's brightness like you see here in this little cartoon. Okay, so for the Kepler Space Telescope, which is the mission that I am going to address in the first part of the talk, Kepler stared at a single patch of sky continuously for 4 years, and that's where this star was discovered. I'll mention the TESS Space Telescope later on in the talk. Okay, so you have this point and stare mission, right? And you're looking for this chance alignment of planets going around their stars and periodically blocking out the light. And you have people looking at this data, looking for that drop. But you also have computers that are doing it too, right? And computers are pretty good at picking out periodic signals, especially in time series data, right? So there was this kind of human versus machine, challenge going on. Like, are you going to be able to find any that the computers missed? Sure enough, we did. So here's a plot showing a planet's orbital period on the bottom axis versus a planet radius on the side axis. So the size of the planet, the planet radius, it's reflective of how deep, right? How deep that transit dip is when the planet goes in front of the star, right? The orbital period is how frequently is it going to go and cross in front of the star. And so, not saying that from this figure here that planet hunters, meaning human eye, did not recover any of these black points. They did recover a lot of those black points, but none of these red points were recovered by automated algorithms. So this is showing the kind of sensitivity and parameter space that the human eye is really good at detecting planets that have orbital periods similar to that between Earth, which is right here, and Jupiter, and between kind of the Earth and Jupiter sizes, right? So it's actually very good at doing those sorts of things. Another thing that the Planet Hunters group is very good at doing is finding things that you weren't actually looking for in the first place, right? So this is where this star KIC 8462852 comes in. And if we zoom into what its light curve or brightness versus time plot looks like, here we have the very first kind of part of this data where you have time on the bottom and brightness on the side. Our users picked this out as it looked like a transit, so a planet transiting across a closed star, but instead of being kind of a normal looking transit, it looked super big. So instead of a transit taking, a couple of hours, this one lasted almost a week, and it wasn't very symmetric. So it's like something that was not circular, that was going in front of the star and blocking out its light. So as the mission went on, the Kepler mission observed it for 4 years straight. You go about 2 years in, and in 2013, in 2011, you find this feature, which is really astounding and remarkable to see something like this after nothing. Like there were a few little blips like that first one I showed you, right? But this one goes down and blocks out about 15% of the light. So this is a huge amount of light. And again, it's asymmetric and it lasts about a week. It's kind of like throws wrenches in any kind of explanation that you would think to explain what could be going in front of this star and blocking out the light. So again, this figure shows the whole light curve here. So this is 4 years of data. So very precise measurements taking every 30 minutes. And I'm going to zoom into this last part right here, which is super exciting, intriguing. That was in the pupil of the eye that I showed you on the logo, right? Where here you don't just see a single transit dipping event, right? You see many events that last for a period of over 90 days. They have variable depths, they have variable durations. You have some dips that are kind of superimposed inside of other ones, like many events are kind of happening simultaneously, right? And the deepest point here, the light blocked was about 22%, right? So if you have a Jupiter about as big as a planet can get going in front of a star, you can block out about 1% of its light, right? This is 22%. So this is very, very massive object. So when you see something like this, the science team, right, was notified by our users. They say, hey, this is weird. And we said, well, that's probably bad data. Let's, move on and find planets. But, it checked out. And somebody said, okay, well, what do we do now that we have this problem presented to us? So you learn as much about the source as you can so you can try and put together a theory on explaining what is happening. So what we did is we learned all about the star itself. And this graph right here is called a Hertzsprung-Russell or an HR diagram. It is a cartoon, but I just wanted to show it to be representative of the kind of stars that are in our galaxy. So most stars lie on this what's called main sequence, which is this diagonal line through the center right there. That's where stars spend 90% of their life happily burning hydrogen to helium That's where our sun is, which is labeled just down from the center, right of center. And then you kind of have different populations throughout the graph. But I wanted to show you here is that our star, right here, KIC 84625. I can normally say that without messing it up. Anyway, okay, is kind of similar to our sun, right? It's a little bit brighter. It's a little bit hotter, right? But in the grand scheme of things, it's not too different. And if you look at different aspects of the star, like is it super young or is it super old or anything like this, like it is pretty normal. It is very, very normal. So at that point, you're like, okay, well, we learned a lot about the star. Nothing actually points us to, what's going on. What is making this star abnormal? So you're like, okay, well, a star would be, a constant brightness, right? Unless something is happening to it. So let's put together several different scenarios. I'm going to put them all up at once for simplicity. Okay. So first of all, let's start on the left, right? Well, maybe nothing's wrong with this star at all. Maybe there's a bug on the telescope or the data pipeline or something like that, right? That could be explaining everything, pretty easily. Okay. So that's definitely a possibility. Other ideas, where in the front? So going from left to right, well, what if it is actually something with the star itself? Maybe it has some weird pulsations or doing some clarity or some kind of things within the star, right, that is making these variable light curves that we're observing. The second idea is, okay, well, maybe it's something that's circumstellar. So that means you have your star and you have something going around the star. So like our sun has planets and asteroid belt and things like that going around it, right? So that kind of scenario would be something circumstellar. Lastly, the last family you have is something that's kind of intermediate. So in the interstellar medium. So you would have Earth, you would have your star, and then your interstellar medium is kind of in between. And what if there is something there that you're observing this starlight through, and that's kind of what's making these observations. So considering all of these, and I'm definitely not going to do a great job giving all of these enough credit because there has been a lot of work done with these. But I did want to, put forth a few scenarios to kind of explain things. Astronomers mostly go to the circumstellar explanation, right? It's something, so perhaps maybe this star was first born or just formed and it has this like debris disk that it was made out of. It hasn't blown away yet, and that's kind of swirling around it and kind of blocking out the light in weird ways. Or perhaps, it's an asteroid belt that we're seeing, and this is actually blocking the light, as we observe it over time. Maybe there's a giant ring planet. So we've discovered like one of these J1407 that's a massive, really amazing spectacle. If you go and look at that data, maybe it's something like, a crazy planet that has this kind of like debris disk that's carrying it along with it. Or maybe you have some sort of kind of recent collision that's created a lot of dust. It's very chaotic and not periodic, and that's what's creating your light curve. And so in all these scenarios that we point to, they all involve some sort of dust or material around the star. And this becomes a problem when trying to explain this star in particular, because of the kind of light that we observe coming from it. So if you consider a star itself, right, so a single star over here on your right, this is what a graph would look like if you graphed its brightness versus wavelength. So what color light you're looking at. It kind of goes up and then it gradually goes down. If you put stuff around that star, what happens is the light leaves the star, it interacts with that stuff, it gets absorbed, and it re-radiates that light in the infrared. So here we have wavelength down here. The infrared is over there on the left kind of side of the right side of the wavelength. So over on that side, right? And you see that kind of orange curve is like above that nominal blue curve right there. And depending on what kind of shape you have that dust in and how far out it is, it'll look a little bit different. But it all boils down to what we call an excess in the infrared. So you just have extra infrared light over here, right? That's indicative of stuff around your star. Now, we didn't observe this with our star, which is like very perplexing and confusing because we have all this, what seems to be stuff blocking the light. You can only imagine that it's some kind of, dust, no matter what scenario you're thinking of as being formed. And so trying to invoke one of these theories to explain it is pretty hard. There's one exception is the idea that maybe there is a comet or a swarm of comets going around stars. So let me take a minute and explain what a comet is. So a comet is an object, this is for our own sun, in a very elliptical or egg-shaped orbit, right? And how this comet's orbit traces out, it spends most of its time very far away from the star. And then as it approaches the star, it actually speeds up and it kind of zips along in, gets slingshotted back out, right? So it doesn't spend a lot of time here close to the star, but actually when it does get close to the star, these comets are like dirty snowballs. And so they start to not behave like, a rock in space. They actually start to sublimate and, outgas and stuff like that. And they get really, really big. They develop these colas, these tails, right? And that is only around this area right here. So a way to work around this idea of not seeing any infrared excess for the star is if we're not measuring an infrared during the time of these dips, then whatever bodies are occulting the light could have moved away and you're just not seeing them anymore. Okay, so this is kind of the picture that we paint. Yeah, you have some swarm of comets that have kind of swept in and blocked the light in really weird ways. Much like the Shoemaker-Levy 9 comet, up here we have this string of pearls, right? Where you would have a single, maybe large cometary body that gets very close to a massive object. Its gravity kind of breaks it apart, fragments it, right? And so you have many, many, many of these objects that are transiting and blocking out the light. So perhaps the system is going through some sort of, late heavy bombardment period. This was our theory in the discovery paper and why it kind of got the name WTF, which actually got it past the editor in the journal. They did not catch it. I'm pretty proud of that. And we actually got some press, and I had fun with this because so comets in our own solar system, right? If Earth goes through a comet path, right? Comets leave a bunch of junk in their way. And Earth goes through the path. The Perseids were just past weekend, right? So that's comes from some comet. I forget its name. I think it has a 9 in it. Anyway, right? So comets leave a bunch of junk in its way, and Earth comes and plows through it, right? And you get meteor showers, right? And I was like, well, if you have this mega comet going around a star, what if there's a planet there? You would have the meteor shower of a lifetime. Anyway, so very shortly after we published this, a colleague of mine, Alice Coolin, had a graduate student, Eva Bowman, and she's like, I have these students that are making these really cute models. We want to model your star. And I was like, okay. She went through and she couldn't do the first part of it. It was not agreeable, but she did a wonderful job in these last 90 days here, putting these, throwing these comets there and modeling the system. It took an enormous number of comets to reproduce what we're seeing in these observations. It's all a work in progress. So it wasn't long after that this article came out, which kind of made this whole story with the star become viral. And it all comes from this idea. So a colleague of mine does work on SETI, so the Search for Extraterrestrial Intelligence, and we couldn't find a natural explanation to explain the stars. We were like, hey, why don't we kind of look and see if there's any interesting SETI signals from this star. And so we wrote a proposal, which was rejected. But then once this article came out, the observatory like contacted us and say, hey, we want to work with you. So anyway, things went crazy for a little bit, like really crazy for a little bit. And it was funny because like when this story came out, I was observing on Mount Wilson, which is in California. You have no cell service. And like I was actually going down to the airport that morning. This story comes out. And like by the time I get into cell service, like my phone was dead from like all the like messages and stuff. Anyway, so what the heck am I talking about when I'm talking about SETI and aliens and craziness? Okay, so first of all, I just want to say, I find it very strange that astronomers and people who study SETI were all searching for the same thing, but like it's kind of taboo to work together. I find that very, very strange. Okay, so what does it actually mean to search for signals of extraterrestrial intelligence? So these are all figures, these are all illustrations of what's called a Dyson sphere. So this is a massive megastructure that's built from an advanced civilization that's either used up all their energy resources on their home planet or they're terraforming outside their home planet. And they need more space, they need more energy. And so they're building out, right? And so you can imagine one of these structures kind of spinning around its host star and how it would produce maybe, some crazy light bursts like we see. All right, well, one thing that we need to make sure that we think about, well, one of the many things, is something called waste heat. You talk on your phone for a very long time, it gets hot, right? You put your laptop on your lap, it gets hot, right? This is called waste heat. Anything that uses energy, right, is going to give off heat. So this is what a house looks like in visible light. You can actually pay people to come out to your house, not like it's happening these days, but in the wintertime. Up north. You can pay people to come out to your house and look at your house in infrared light, and they'll tell you where you have insulation problems in your house because they see where this heat is getting out, right? So like if you're invoking aliens, right, and you're just saying, okay, well, yeah, we invoke aliens, then we can also say, okay, well, this house star is perfectly insulated except for the backside that we're not seeing, and then you can kind of get around this lack of infrared excess. So the infrared is this heat here. Okay, so just to iterate that point, extraordinary claims require extraordinary evidence, and with 3 parameters, I can fit an elephant. And my friend Joe Lama made this cute little graph, and with sound, it should be playing jingle bells, right? As you can see, as the reindeer and the sleigh and the things are like kind of falling off, right? That's an asymmetric, showing the light profile down here, right? It's very asymmetric kind of, jaggedy light profile, different than a planet, right? Okay. Okay. Just a little bit on searching for intelligent life. I actually get to do this, so I wanted to tell you guys just real briefly what it's about. So you go to this like really remote, crazy place in West Virginia called Green Bank Observatory, where they have the largest steerable radio telescope, which is shown here. And over here on this side, I would get in trouble if I just, they learned that I took this picture because you're not even supposed to have your airplane mode cell phones on because that creates disturbance. That's anything, nothing, people, nothing. Like everything's in a Faraday cage. It's crazy there. But I thought it was really cool to see the data coming out and like what it was actually doing. So what we did here is we're calibrating the instrument and we pointed at Mars, right? And we had a signal. And we have a signal that's not just a straight signal. We have a signal that's a little Doppler shifted, right? So there's some kind of motion to that signal. So that's kind of cool, right? Like, we're detecting like signals from Mars, right? Like technology on Mars is beaming it back to Earth. Like we put that technology there, right? So that's not the aliens, right? Like they're not sending it to they're sending it to, deep space, whatever they call it out there in California, right? But we're intercepting these signals right? And we can tell that there is technology on Mars. We can do the same thing for the Voyagers and now Voyagers. Yeah. And so this is kind of the theory that there is. If there's some kind of like advanced civilization that can build these megastructures, they're going to communicate maybe through radio waves, and perhaps it's leaked enough and we can intercept that. So anyway, I thought it was pretty cool. Okay, so now things get a little weirder, believe it or not. Okay, so you guys might know Brad.
Oh, yeah.
He might be online. I don't know. Hi, Brad. Okay. Brad was a professor here at LSU. He's still an emeritus professor. He's out in Arizona now, living the good life, but it's hotter there. And he is one of the world's like only remaining experts in this very, very old data set called the Harvard Plate Stacks. So this kind of data set, I say is old, like, I mean, I'm talking about photometric plates, so these glass plates that are covered in emulsion, and that's what observers used to put at the focus of their telescope and like take exposures, and then you could take measurements like one of these Harvard computers over here, Annie Jump Cameron. They used girls for computers because we were better at everything. Just saying.
More patient.
More everything. Anyway, so Brad's like, ooh, this is interesting, right? Like Kepler observed this for 4 years. What was it doing 100 years ago, right? This data set has data going back 100 years. And so he went up to Boston, from here, he went up to Boston, and he dug out these plates and he made these measurements. So this is what he found. And I have a quote here from him because he just says it so eloquently, but I want to explain the data here first. So here's 100 years of data. So the data for my star, the WTF star, is shown in blue. There's two lines. You don't care about the difference between them. They're both going down. And the difference between the left side and the right side is 20%. So it's 20% brighter 100 years ago. The other kind of faint things there are reference stars, calibration. They're showing that they haven't changed. It's a way of showing that, okay, it's not all the stars are going that way. It's your star is fading and everything else is continuous. So this quote over here mentions a couple of things. He mentions first the idea of Occam's razor, right? Occam's razor says the simplest explanation is the right one. So if you're going to invoke some crazy idea of having comets come and explain your short-term dips that we saw in the Kepler data, right, as we did, then you also have to invoke comets to explain what is happening here. So that means instead of like a few thousand comets coming in front of the star within those 4 years of Kepler, you now have nearly 1 million stars or comets, right, perfectly orchestrated to come in between you and this star and block out the light in this pattern to show this secular dimming. Plus, you're having the dips as well, right? That's a lot, guys. Like a lot. But who's to say like our solar system isn't like the neatest one out there, right? I mean, that could just be normal. I mean, we haven't seen this in front of any other star, but nature can be weird, right? Needless to say, when this result came out, it was not received very well by the astronomical community at all. You're looking at a data set that comes from, photographic plates that are 100 years old. Like, how reliable can these be? And okay, well, I mean, you can, have a bunch back and forth and da-da-da-da. But a couple of colleagues of ours, Ben Monte and Josh Simon, said, ooh, we have an idea. We can use the Kepler data set, not the one we saw the dips in, but their calibration frames, and we can measure the actual stars, actual brightness over the 4-year period and see if it's changed in that 4-year period. It's not going to tell us about the past 100 years. All right, it'll tell us about the past 4 years and see if that star is different in any way as well. And so I actually saw Josh right after he submitted this paper, again on Mount Wilson, which is kind of weird. He was like, yeah, we did not expect that. So what they found in the 4 years that Kepler observed it is that, all right, I'm missing a plot. this star dropped in brightness during those 4 years by 3%. This is not counting the dips at all. This is just overall like baseline brightness, right? Because this is a digital data set of, a couple 100,000 stars like in the Kepler field, they were able to do some really robust statistics saying, okay, is it this part of the chip, these kind of stars? Like they did all sorts of tests. And they were able to determine that this star, the entire light curve there, was significantly dimming versus any other star there by 8 sigma. So like that's like 8 times the standard deviation from the mean, which is like, I mean, it's like it's in its own league. You can't do that. So that's pretty remarkable. So that's 1 in 500 billion. I have it written down here. Pretty unprecedented. All right. So this star dips in very weird ways that we've never seen before, and the star dims also in weird ways that we've never seen before, right? And we really want an idea of like what is causing this, right? We also want to take under consideration Occam's razor. We're folding all these things in. But the best way for us to learn about what's going on is to catch the star dipping in real time. Okay, so when the Kepler telescope observed this star, it was observing it, and then after 3 months, you would download all the data, and then like after a couple months, people would get the data after, like it would be processed. Like you wouldn't get it in real time. You'd learn about things afterwards, right? So the other thing about the Kepler Space Telescope is that as amazing as it was, it could measure the brightness of something. If you were to light up the entire Empire State Building and have like all the blinds open and light it all up, and if you're to pull one of the blinds down by 1 inch in one of the offices there, then that would be the amount of flux decrement that Kepler Space Telescope was able to measure. Like it's really, really good at doing this. But it was only a single color. And I'll explain more why this is important in a little bit. But we can design a program that will tell us a whole lot more without some of like the other things that we need. The problem here is that we don't know when these events will happen. As you can see here, there's nothing periodic in this data. So, I mean, if you're looking at all these events, none of them really look the same. You can't predict when the next one's going to happen. So you basically just stare at this thing the whole time, which is really hard and not very cost effective. But thankfully, there's actually an observatory that is specialized in time domain astronomy, which is really big these days, gravitational waves and that sort of thing. But their logo is "We keep you in the dark." Anyway, what they do is they have all these telescopes. They have a northern hemisphere network and a southern hemisphere network, right? And you put your scheduling request into their main system, right? And that's one brain of a system. So like it knows like if you're observing in Texas and the sun's coming up there, it'll switch over your observing program to the telescopes in Hawaii, right? And so on. So like, continuously, if you're longitudinally like, separated around the globe, they will keep you in the dark. There's never a place where you can't observe your star. Unless the sun's in the way, then nobody can observe it. So this is kind of what we needed, but we needed also something that was not dedicated, but something you could do, say, Q observing. And this observatory also does that. And so we actually kickstarted the Kickstarter and raised over $100,000 to study this star more. And that was kind of an amazing project because we now had like a star that was discovered by the community, by like citizen scientists. And now like, this kind of theme was ongoing with this next kind of iteration of what was going on. And so we set out to collect data on this star, and here's kind of showing like what our measurements look like at first. There was a lot of nothing, guys. And yeah, it was Yeah, we just waited for a long while. And then we noticed that brightness was going down on May 19th, 2017. We're seeing it down at 2% here. And that's kind of where we hit the go button, right? We emailed all of our colleagues. We posted on Twitter. We're like, hey, if you're at the telescope tonight, can you grab a snapshot of whatever instrument you're looking at so we can, we can study the star? Because now you have a dip going on, right? And these are with, kind of smaller, we can learn stuff from here, but you can point your big telescopes at it now, the ones that cost like, $100,000 a night to use, like Keck telescopes, right? You can get a snapshot of that and learn a huge amount. Okay, so fast forward ahead, that was May of 2017. Here we have data going back from 2016 all the way to 2019. And in the center here, there's about 9 months or so where it's labeled the LC family. So here we decided to name the dipping features, just like asteroid people get to name asteroids. We decided to name the dips because I didn't like calling them the day 1800 dip. It was really stupid. So we have LC, Celeste, Scarbray, Encore, Carl, Soup, and Evangeline. And they all have meanings behind their names. You can go and look them up, but I think it's really cute. There are a couple of here that are named after old lost cities, right? And the idea here is that you have a star, something's happening with the star. This star is such distance away, right? Whatever's happening with that star at such distance away, it takes light a finite amount of time to travel from that star to our telescopes, and so we observe it, right? So, we're trying to find out, we're collecting that light now saying, ooh, that's weird. And we're, getting that light now, we're trying to find out what happened, 2,000 years ago when that light left the star. It was 2,000 light years away. Which is kind of cool, right? Because that's what these old lost cities, and researchers are trying to figure out those stories too. Anyway, so we have this series of dips, and I'm going to kind of go into it a little more, and all the contributions from a huge response from a whole bunch of people. Yay. Okay, so main results. So I mentioned that bug on the telescope or in the data reduction pipeline. I don't want to mention that so that was a real concern because most people, when they first look at it, they say that's not good data. That's what I said when I first looked at it. So what this is showing here is dates on the bottom for each one of these, and then how bright it is on this side. And all the different colors are different all the different colors of data points and different colors of light. That's not important right now. What I do want you to notice is that at around this point right here, kind of like in the middle of each one of these, they all go down. So if you're observing it at all these different telescopes, it's all going down, then you're not going to have a bug in your software or at your telescope or anything like that for all these different observatories, right? So it's kind of checked out, okay, well, we have found it here, then it's probably likely to have be real up there. So it's not an artifact. Another point that came out from the results is that there's no real clear pattern, right? And I'll kind of show a little bit more in some of the patterns here, but the only thing that kind of matches up is Scarbray. And this is showing Scarbray right here. We have time on the bottom, that's in days, and brightness over here, where that solid line there, that's not a model to the data, that's the Kepler data. That's what Kepler data looks like. It's really good. And the different like black and blue and red points are just data from different telescopes. Like I said, you have them longitudinally dispersed around the globe, right? Where you actually get maybe a bit of a signature that goes down the center of this kind of 2-week long dip, maybe. That was the only kind of pattern that we were able to pick out. Another thing that we were able to learn, or maybe not learn, is that we got some very high resolution spectra from the Keck telescopes on a few different occasions. we're able to measure the radial velocity of the star itself, and we're also able to measure these interstellar lines, so these very sharp features inside of a very broad feature. And we saw there was nothing. It was very underimpressive. there was no difference in radial velocities or variation in line profiles of the widths or anything like that for either of those data, both in and out of dip. Another really cool thing that came out of this event here is shown here. So the WISE mission is now called NEOWISE. I don't know. It's had many names. So it was originally a all-sky survey to detect asteroids. So it was looking in the infrared, and it's still up and flying, and it's doing its survey thing. And so it was actually doing its survey thing, and our star followed in the field of its survey right here. Notice that's where Elsie is. So at day 85, we got some observations in the infrared. And so while WISE is doing this, occasionally it has to go and point away from the moon, like the moon gets in the way. And so it's like, ooh, I have to do a moon avoidance procedure, and it goes and it points at some random spot in the sky and takes data for a little bit on that until they can go back and do its normal thing because the moon just moved out of the way. Okay, so when the moon was in the way, it actually did that. It actually pointed to where our star was. And this was when the LC dip was happening, that very first one. So here we have a couple of data points from two of the WISE filters right here. And I mean, long story short, it doesn't show any difference from the in and out, which is kind of disappointing because like you kind of want this infrared excess to explain the stuff that's in between you and the star. But it's still a really cool coincidence that that's how the telescope data came about. Another result that came out of it, we looked at polarization in the direction of this star, found out it was pretty normal. That's what this shows. But polarization would indicate any presence of dust grains, which gets polarized, or dust grains polarized light, and didn't show anything abnormal. Okay, so the cool part right here. So this is showing that first LC dip. And I kind of want to take a minute to unpack this plot right here. On the bottom is time, so that's like day down there. And on the side axis, you have how bright it is. The different colors mean the different color of light. So B is like blue. R is, like, I don't know, just go from the colors that are there. That's the rainbow. I don't know. This is astronomers' codes for how they color light. Anyway, and you can ignore the symbols from now. Those are just different telescopes. And so like, we just, again, they're longitudinally dispersed, getting data from different telescopes. Anyway, so what this is showing here is super amazing. This is what the Kepler Space Telescope, with its amazing precision, couldn't tell us, right? Is that as this star dips, right, it goes further down. It blocks out whatever's coming in front is blocking out more light in the blue than it is in the red. You guys see that? Okay, so the astronomer's word for this is chromatic, right? So if you can imagine, again, with like your star and your planet going around your star, right? If you're looking at a planet going around the star, if you look at it in blue light, it's going to make a drop, say 5 units, right? If you look at it in red light, it's going to block out the same amount of light, right? Because it's an opaque object that's going in front of your star, so probably 5 units too. But in this case, you're not seeing the same drop in light. So this is telling us that this is not an opaque object. This is some sort of optically thin dust. And this is really cool, right? Like, wow, we can actually measure this, right? And tell us about the grain sizes and the composition of what is coming in front of the star. And so that's what we did. Another thing that was able to come out pretty much about the same time is this long-term dimming, right? I told you, found in the Kepler Space Telescope. Brad Schaefer originally discovered it. And then there's like these slow monitoring campaigns since the star was discovered in 2015 and so on. And we're also seeing this chromatic dimming, right, for this long-term trend. So that means like the blue is dimming faster than in the red. So that's kind of what's shown over here in this panel. And this can also tell us that, if you're dimming more in the blue than in the red, right, that means it's some sort of optically thin dust that's getting in the way and blocking the light. Okay, so as I mentioned, it's really hard to study something when you don't know what's going to happen next. So here we have the Kepler data in purple, right? Nobody was looking at this star for a while, and then we are all looking at it, right? Because aliens. But let's make a really bad guess, right? Let's go and say, all right, well, in the Kepler data, there was a big, dip, like kind of halfway through, and then there was another big cluster of dips, like kind of in the end. What if that was the same thing, right? And so we'll assign that an orbital period of something, whatever it is, right? And I say it's a bad guess because they don't look like each other, right? But they're kind of the same depths. And, if you have one thing that looks singular at first and then it goes around, it could have grinded up and kind of pulverized and moved around and then spread out. Who knows? Okay, so the time between those two events is 750 days. So let's kind of jump forward in time. 750 days later, no one was looking at it. But then 750 days later, that was the LC family of dips. That was pretty exciting, right? Okay, well, 750 days later, what happens in fall of 2019? So that's what brings me to the TESS mission. I mentioned this before when I was talking about the Planet Hunters project, looking through Kepler data and TESS data. TESS is like, it's a different version of Kepler. It's doing different things, same kind of idea, point and stare, but it's not pointing at the same field for 4 years. It's doing all sky, and it takes these snapshots of a different strip of the sky for about 30 days at a time. And so depending on where your target falls, it can fall in a spot where it gets observed a couple 30 days in a row, or however it kind of goes. It's actually very complicated now. But it ended up that our star, considering the whole sky, right, was observed in sectors 14 and 15. Yes, but it's like the exact multiple of 750 days that this space telescope was observing it. Like, we got really lucky again. Okay, so this star actually happens to be one of the Kepler Ghost scientist. Garrett's like, he really likes this star, so he's made like all the tutorials and stuff for their programs using this star. It's kind of cool, but he posted on Twitter. He's like, yeah, look, here's what the sector 14 data look like for the star. I don't see anything. And it's like, okay. Well, then a month goes by, and it seemed like everyone forgot about it. So I kind of go in, and I'm like, I kind of don't know what I'm doing, but I think I see something. And so I'm like, here, this is what I see now. And he's like, ooh. Let me see. I'm going to point out with my mouse, right? So there's a little blip right there, and there's a bigger blip right there. And you can kind of see this one's up close. I can't see which one that is. Okay, so this is super cool, guys, right? There's two events. They're 10 days apart from each other. That's weird, right? Because there's nothing else like in the other 10 days. The other weird thing about this is that it kind of looks like a planet transit, right? It's not like asymmetric or like anything weird. It's kind of like the depth you would, think it was, and so it kind of looks planetary. What was a little strange about these is that they do last for a long time. So most planet transits last for a few hours. So that's the time it takes for that planet to go across the star. these last for 24 hours. So it's a little weird. Anyway, this is where we're at right now. So the LC family of dips, right? We had nothing. We kind of had to bump up in brightness. And then we're still monitoring it over here, and that's where the test is. You see it in black over there. We actually had ground-based data at the same time we had test data. We're totally winning here, right? I think this is so awesome. Okay, so this is what we have here, right? And we can learn a lot from this, just like it is, right? I mean, we're observing from the ground using these really not tiny, 40 centimeter telescopes. So not tiny, but not big ones or anything. We're able to get really good data and actually catch something on order of this time scale, which is pretty amazing. And this is the deeper one of the two. And just to kind of zip ahead, I wanted to show you. Yeah, I think it's this one. So what this is showing over here, this graph, you have the different colors on the bottom are the red is like red, and the blue is like blue. So forget those labels. Again, right? Before when I said the LC dip was chromatic, right? The blue went down more than the red, right? And this dip right here, there's nothing like that, right? They're the same, it goes down the same amount, which is kind of that's interesting because this actually looks like a planet instead of some blob of stuff that's going in front. Anyway, because these test tips look like a planet, I had an undergraduate that was working with me, and she just left for grad school at Georgia State. Now there's a graduate student working to kind of finish this up, kind of modeling these transits to see what the period of a planet would be if these were actual planetary objects. And yeah, so that's kind of where we're at. With that, there we go. I put in an arrow. All right. So just to summarize, right, that I really don't think that, saying that aliens can explain your data is ever going to be the right solution right away. Hopefully one day we'll be able to say, yes, that's aliens, right? But I don't think it's going to be discovered like this. Especially, in this way. It's so the current understanding is dust, but it's proven to be very challenging to fit all this dust in front of the star without having an infrared excess detected around the star. Because the more dust put in, you can fiddle with your geometries, and then you have to have your dust production scenarios. So especially for the LC family of dips, these dips all lasted for longer than a week, some 2-3 weeks. If you have an object going in front of your star and it's kind of sublimating and outgassing and everything, making all the material that's blocking the light, that material is going to get blown away within a couple of days, 3 days maybe, from radiation pressure from the star, right? So something has to be replenishing it, right? And we actually don't know what kind of mechanism can do that on those sort of time scales. And so that's also a challenge, as well as the geometry of the whole system. And I don't think we've actually ruled out the scenario with something intermediate, so an interstellar medium, so something going between us and the star, just in space like that. But honestly, I can't really wrap my head around how that works, and it doesn't work for any other star that you look at. Space is really big, right? You're yeah, of course that could happen, but we don't see it in any other star, and Kepler looked at a couple 100,000 stars, and we don't see anything like that. it's hard. It's very difficult. And I think there's one person in the camp that is still in the camp of stellar variability. So we're not entirely all in agreement on even the family of explanations for the star. It's definitely a really fun thing to study and work with because we just don't know what it's going to do next. Yeah. So I can take questions now.
You have an ulcer yet?
Huh?
You're working on an ulcer with us. I have a question. Actually, several. First thing, has anybody asked for time on the web?
Yeah, we asked for time on the web and we should be getting it here soon.
Because I'm thinking maybe infrared, it might show some type of smaller object.
If anything's going to see it, web's going to see it, right?
Yeah.
Like, I mean,
And
that's,
it's 2,000 light years away, so I don't know if it would, the size of the sun probably still won't image the surface.
no, we're not going to be able to like resolve it, like take a picture of the system itself,
Oh,
right? But we'll be able to get those measurements. Remember those curves of wavelength versus brightness. So
one thing I'm thinking, and that's probably totally wrong, but since you're losing brightness, the brightness is related to the heat that the star gives off, right? Am I wrong or right about that? Is there some relationship there?
yeah. Mm-hmm.
If that's the case, do we see any CMEs or anything else going on that would allow something to be thrown up into space large and then condensation of some sort?
Yeah, no, I mean, there's no real big brightening episodes at all that we've seen, right?
So they thought about that. I'm just thinking that.
Yeah, I
maybe-
mean, I have not intentionally, but I intentionally left out a lot of things because there's a lot of work that goes into a lot of different parts
My
of
thought
studying.
is since you're losing over
this
a long period of time heat or brightness, that there could be some relationship to that star and what's happening around it. But
Right.
what it is, I'm totally at a loss.
Question.
Mhm.
So I didn't quite hear you. Did you say you did get time on the James Webb?
Mm-hmm.
You did?
Mhm.
Okay, and second question is, what's Dr. Schaefer's hypothesis? What camp is he in? Has he?
I haven't talked to him in a while about it. I don't know if he's online.
I was just wondering. Because you
Um,
just said one camp is about it being a variable star. I didn't know if that.
Oh no, he's not in the variable star camp. I think he's in the circumstellar camp. I don't know. Yeah, I haven't talked to him in a while. I'll give me an excuse to talk to him now that you brought it up. He has opinions.
So when you say circumstellar, what would that be? Just dust?
Yeah, so like something around the stars. So I gave a couple of pictures in the beginning of the talk of different kind of scenarios. So maybe you have an asteroid belt,
Okay,
Or,
that's the
a
circumstellar.
family of comets, right, that have, fragmented and string of pearls kind of going around, or maybe you have some sort of super Saturn object or something like that. Yeah. I mean, to get the dimming and the dips, you're kind of talking about like your central star, and then perhaps you have like a swarm of comets that are in this, I don't know, going in this kind of elliptical orbit. But they've broken apart. They're kind of pulverizing and grinding. They're leaving a lot of material around. So they have this kind of torus as well. And the torus could be like kind of leftover torus. That could be doing the long-term dimming maybe. And then you still have these clumps that are traveling through that torus. I don't know. But then, I mean, it gets really hard to fit that all under no infrared excess. And so
Well,
that's,
what year do y'all have James Webb? Or is it 2024?
it'll be the next cycle. Yeah.
Well, that's exciting to be
Yeah.
accepted for that.
Uh-huh.
And what you're gonna do when it shows a little green men staring back at you?
We'll get more data and make sure. Yeah.
How long was the length of time for the well?
Hmm?
How long a length of time that you get for the well?
It is highly competitive, and scheduling is very difficult. So you have a 1 in like 15 chance of getting when you submit a proposal, and then when they schedule it, you're kind of at their mercy. And you get the minimum amount of observations you need to do your science. So if you want to go and you want to take a spectrum of your star, right? You do calibration frames, you do snapshot spectrum, and then it's off doing other stuff. Yeah. So, huh?
I said maybe not too long now. I mean,
Yeah.
that's good, that's good. Yeah, okay.
Mm-hmm.
What possibly though is if given the dust hypothesis or other materials, it seems like the dimming is happening very quickly. Or some other clouds, I guess you could say, or material that connected to sharp dimmings. I mean, it would have to be a very, very active cloud that's causing some kind of rapid change.
Yeah. Yeah. So, I mean, nothing happens on those timescales astrophysically, right? So stellar revolution does not happen on 100-year timescales or anything like that. And so that's kind of like where we're following to, but like, yeah, I mean, and 20% is a lot for, yeah, I agree.
Unless there's some long-term variability in the star, we just haven't seen it up its own
Right.
cycles.
I mean, it looks like a normal F star. Like, I mean, there's nothing weird about. There's nothing weird. It's spectral lines,
not
it's not
G.
its elements, not its age, not its galactic motion. Like, yeah. So we can't say, okay, oh well, it has these, something, so perhaps it has, non-radial pulsations. This is ejecting stuff, and no. That's it.
Well, how old is a star?
It's a few billion years old.
But stars that, as you move up the scale, evolve faster.
Yes. It's still a main sequence star.
Yeah, but that doesn't say it will stay as long as our sun will. Our sun is a G, so
Yeah, our sun will stay a main sequence star for about 10 billion years. This one will stay a main sequence star for about 4 or 5 billion years.
that has some influence on it. It's just
There's lots of
evolving
lots of other
faster
stars like that out there, and they don't,
They don't do this sort of thing.
yeah. So
Have y'all adequately accounted for the observed dimming over time? Have you adequately addressed the observed dimming of the star as a whole time?
what do you mean?
Like 100 years ago, it's 20% brighter than it is now. Have y'all found some explanation for why it's dimming?
No, yeah, that's what we were just talking about, and Brad makes a good point in his paper. He's like, stars don't do that, right? So like, you got to figure out a reason why it's doing that, and it's probably got to be connected with why it's doing these weird dips too, because you can have two weird things
How strong
and
is that
explain them with two weird things that are entirely different.
Just how strong is that probably?
Hmm?
How strong is the probability that they're connected?
I mean, it's Occam's razor,
Okay.
right? So
It'd be a lot easier if it was.
yeah.
Okay.
Yeah, I mean, yeah, a lot easier. It's probably the right reason.
I don't want to monopolize, but what about chemical composition? Is it
It's
much
got
different from what our
solar
sun has?
It's
or-
got solar metallicity. So it's very, very similar to our sun.
So it's not showing any, because of some lack of maybe hydrogen or helium
Mm-hmm.
that's causing something going on in the core.
Right.
No matter where you go, you get stuck, don't you?
One more thing.
Yeah.
Are you willing to say something about the newest project that you and Matthew are working on? Some of the papers may not have the letter of the sun.
Oh yeah. Okay. So first, before I do that, before you go, you should check out my rock. Okay, I brought it in for kind of show and tell. Yeah, try and pick it up, but be careful. Past couple of years, we've been doing a lot of development on a project that is to put a telescope on the moon. And this would be a kind of smallish telescope that would be attached to a lunar lander, being delivered to the moon by the Eclipse program. And the science, what we want to do is to study exoplanet atmosphere. So it's going to be tuned to the kind of near UV blue area. And we're going to be measuring the depths of transiting exoplanets and basically the Rayleigh scattering in their atmospheres. And this is advantageous to do it from the moon because, one, you can't do it from the surface of Earth because we have an atmosphere and we can't see those colors of light. If you put a satellite into LEO, low Earth orbit, then you have the Earth getting in the way every 45, 90 minutes or so. And so you have these gaps in your data. On the lunar surface, you have a stable platform, right? You don't have to worry about pointing controls, gyroscopes, in the air. You're on the ground, right? You just point up and you observe. On the lunar surface, you also have continuous observing for about 14 days at a time. So this is about the length of a lunar day. So we observe in the daytime, that's when we have power. And then hibernate at night, and then you can wake back up during the day. If we had extended power, we can do it for longer. I mean, in the nighttime, but we probably can't. That's really expensive. You just want to keep yourself warm so you don't die at night. And so currently, we're looking to go to the Schrodinger Basin, which is on the far side of the moon, for our kind of prototype. And then launching our main program in about 4 years, 3 to 4 years after that. Oh, not
Who's
after that,
funding
from
it?
now. Yes.
Who's funding it?
So right now it's funded by the Moore Foundation. So we have, so I'm the PI and I'm working with a private company called Astronetics. And let me see, Colorado, Boulder, they're doing the telescope design and the instrumentation. I have collaborators at Mississippi State, Caltech, Matt Penny here, and the SETI Institute in California. So another kind of side project that we're interested in doing on studying exoplanet atmospheres and the production of hazes in their atmospheres, because it's a kind of big puzzle in the field right now. Is a colleague at the SETI Institute is really interested in comets and asteroid work and planetary defense as well. And the moon gives you a really great spot for viewing a lot of the sky that you can't get from other places. And so we're really looking forward to, all of that. Yeah. And we're putting telescopes on.
That's gonna be fun. Get the telescope on the moon.
And you don't have Starlink in the way.
Yeah, well, there's going to be a lot of junk in the air, the moon. But everything they're putting up there now is like they're all looking down at the dirt, right? We want to look up because we're astronomers. Not to say the dirt's not interesting, but it's lunar dirt. But
Okay, we have any other questions? Thank you. Well, thank you. That was
Just say that that concludes the poly portion.
That concludes our program for the August meeting of the Baton Rouge Astronomical Society.